Let's look at another example of a polyprotic acid. In this case, carbonic acid. This is a little more typical of a polyprotic acid. They're usually weak for both dissociations, which I can tell by looking at these K values. They're both really small. This was a little different when we were looking at sulfuric acid. Sulfuric had a pretty large Ka1. The first dissociation was strong and the second was weak, so it made calculating the pH of a sulfuric acid solution pretty manageable. We could just go opposite log of the original molarity. The second dissociation was really insignificant. Well, here I guess they're both kind of insignificant, right? I mean, they're both going to give a very small amount of hydrogen, but I still have to figure it out so I can calculate the pH of the solution. Let's write dissociation equations. Let's kind of figure out what it means by saying Ka1 and Ka2. For the first dissociation, we would have the carbonic acid. We'll go double-sided arrow since it's weak. It'll give up its first hydrogen, and the other ion is the hydrogen carbonate ion. In the second dissociation, the hydrogen carbonate ion will release the second hydrogen, and the other product is carbonate, -2. Notice that with these polyprotic acids, we don't just split off the two hydrogen right away. It's one at a time, and they often have different K values. The first hydrogen comes off easier than the second, although even the first is still reluctant because that K value, Ka1, is still really small. So again, we could kind of make note that these are both weak. Weak acid dissociations because those K values are crazy small. So we somehow have to figure out the amount of hydrogen in the solution so we can get the pH. The other thing they ask me for is the equilibrium concentration of all species present in the solution. That kind of means what's the concentration of all particles that are present in the solution? Well, since this is a weak acid, we're going to have some of this hydrogen carbonate present. The neutral H2CO3, that will be present. And actually, I can kind of guess right now that it's probably the most abundant of all those particles listed. That would be different if this were a strong acid. In a strong acid, the original would dissociate 100%, and we wouldn't have any of the original neutral acid. It would all dissociate. Not the case here. Okay, so I'm going to have some hydrogen carbonate neutral molecule. Obviously, we're going to have some hydrogen. We're going to have some of the hydrogen carbonate ion. And we're going to have some carbonate, -2. Because again, here's the deal. In the second dissociation where we formed the hydrogen carbonate ion, not all of that goes forward. We're still going to have some of that hydrogen carbonate ion present. And I can kind of predict right away, of those four particles, the one that's probably going to have the smallest concentration, carbonate, CO3 -2, right? The carbonate isn't formed until the second dissociation, and that K value is crazy, crazy, crazy small. I'll get a little bit of hydrogen from both, so we'll add those up when we want to do the final pH. I'm just going to guess qualitatively right now that the most abundant particle is the neutral carbonic acid molecule, because even that Ka is really small. And the least abundant, I bet that's going to be carbonate, CO3 -2. Let's see if our assumptions are right. So since the first is weak, we got to do an ice table. So both of them are going to require ice tables. My equation for the first dissociation, and we can leave water out. I mean, water's not going to be part of my equilibrium expression anyway. Plus hydrogen carbonate ion. We're going to ICE. The initial molarity is kind of random, but it's fine, 0.18. Initially, no products. This is a very typical weak acid problem. We have to go forward. These will go up by x. So at equilibrium, I'll have 0.18 minus x, x, and x. I have Ka1. Ka1 is 4.3 times 10 to the negative 7. Small. That equals x to the first, x to the first, all over 0.18 minus x to the first. And again, you might be getting good enough that you can simplify this right away. Like I bet some of you just wanted to go x squared on the top. That's fine. You can plug that in right away as x squared. And I bet some of us are thinking here that we'd really like to do the 5% rule, right? Because I don't feel like solving this quadratically. That k value is really small, so whatever x is, it must also be really small. This really simplifies your math. I got to cross multiply yet. I'm going to cross multiply these guys. 4.3 times 10 to the negative 7th times 0.18. But then that equals x squared. Well, that's not so bad, right? Then I'll take the square root, and I get x as about 2.8 times 10 to the negative 4. So I've cross multiplied. That equals x squared, so I just took the square root of both sides. 5% rule. I'm thinking about it. That x is really, really small, 0.00028. When I did my math, I just used 0.18 for the carbonic acid. Yes, it's going to go down, but that x value is not 5%. So we can say 5% rule. Check. I qualitatively checked it. I wanted to make sure that x came out to be something small. And it does. Okay, so now technically I could plug x back in and I could get the concentration of all three particles. The only time that you will see this carbonic acid in either of these two equations is right here in the first step. It's not present in the second step. Now these two, the hydrogen and the hydrogen carbonate ion, those guys are going to change a little bit in the second dissociation. So the only real equilibrium concentration that I can make note of at this point is just the carbonic acid. It'll be 0.18 minus x, which again, that x is so small that if I really just leave two sig figs, it doesn't change. So I don't know, maybe I could go like 0.1797. It's really small. X is crazy tiny. Okay, does that make sense? You know, they eventually want me to get the equilibrium concentration of all four particles. This is the only one that I can really make certain at this point. The original will dissociate a very small amount. But I'm not quite done with hydrogen or carbonate. I get that they're X, but in the second dissociation, I'm going to get a little bit more hydrogen. So I'm probably going to have a little bit more than this 2.8 times 10 to the negative 4th. That hydrogen carbonate ion, that's going to go down a little bit. In the second dissociation, some of that goes forward and gets consumed. So the final concentration of this hydrogen carbonate ion should be a little bit less than X. So really, this is the only one that I'm certain of at this point. We have to do another ice table. Because again, the second dissociation is so weak. We get to do another ice table. This is a good thing. It's fun. Okay, so here's the second dissociation. It's that hydrogen carbonate ion. Da-da-da. It'll continue to release a little bit of hydrogen. And here's the first time where I see that carbonate ion. It's a product of the second dissociation. So we're going to ICE. And now watch what we do for our initial. It's not 0.18. That 0.18, that was the hydrogen carbonate, the carbonic acid solution. As it goes forward and produces some hydrogen and some hydrogen carbonate ion, which we calculated to be X, that's what I put in my second ice table. The amount of these two particles produced from the first dissociation is X. We're putting that in down here. It's 2.8 times 10 to the negative 4. It's not 0.18. That was just the original carbonic acid. And we're going to put that in for hydrogen too. They were both X from the first ice table. Times 10 to the negative 4th molar. The carbonate is 0. We did not form any carbonate in the first dissociation. But to kind of catch that in my second ice table, I use the values that I would have calculated from the first because they're still going to change a little bit. We're going to shift it forward. We're going to consume some of this hydrogen carbonate ion and we'll produce a little bit more hydrogen along with some carbonate ion. So at equilibrium, we can plug this in and we have our second K value. So this is 2.8 times 10 to the negative 4th minus X, 2.8 times 10 to the negative 4th plus X, and X. Ka2 was crazy small. 5.6 times 10 to the negative 11. Yikes. And again, I will set up our ice table. That equals products. 2.8 times 10 to the negative 4th plus X times X. They're both to the first. You don't have to write ones in. And on the bottom, I have 2.8 times 10 to the negative 4th minus X, all to the first. Again, a little different look to the ice table. Often we're used to seeing these weak acids with 0 as both products. This time we have some hydrogen. It came from the first dissociation. So whatever we have, we still put that in as our initial. Okay, that K is super, super tiny. So there's no doubt in my mind that whatever X is, it's going to be really small. Let's get rid of both of them. If we add or subtract X and it's small, maybe it's insignificant. How do you like that, huh? Because then really these guys will cancel. And excellent. X equals 5.6 times 10 to the negative 11. Well, that's not so bad. And again, I'm going to think about the 5% rule. I know that I was starting with a pretty small number, 2.8 times 10 to the negative 4th, but X is crazy small. There's no way that those differ by more than 5%. 5% rule was my best friend there. Check. I love it. Okay, so now we can figure out some more of these concentrations. We can plug X in. Here's the final hydrogen carbonate concentration. It's 2.8 times 10 to the negative 4th minus X. Which, to be honest with you, X is so small that it's, virtually insignificant. I have to leave a couple extra sig figs to even see a change. 2.799 times 10 to the negative 4th molar. Super small. Now we finally have hydrogen. I produced a little extra hydrogen in the second step. But again, if I plug this in my calculator, it is like almost insignificant. 2.8000 times 10 to the negative 4th molar. Did I get a little extra hydrogen? Yeah, but it is insignificant. It really doesn't change my hydrogen concentration from the first step. And here I finally see the carbonate ion. minus 2. He is X. 5.6 times 10 to the, negative 11th molar. Okay, so there's part of it. One of the things that they wanted me to do was calculate the concentration of all ions in the solution. Here's all 4 of them. And my original assumption was right. If even the first dissociation was weak, it means that most of the particles stay neutral carbonic acid. By far, that's the greatest concentration. I also assumed that the smallest was going to be the carbonate ion, because I don't see that until the second dissociation. And the second dissociation was so weak that K value was crazy small, 10 to the negative 11th. And yep, by far, my carbonate ion has the smallest concentration. Now, these guys in the middle are kind of interesting. Yeah, I do get a little bit extra hydrogen from the second step, but it was virtually insignificant. Same thing with the hydrogen carbonate ion. Yes, I consumed a small amount, but virtually insignificant. So the last thing they wanted me to do is calculate the pH of the solution, which then, easy, right? pH should be opposite log of the hydrogen concentration. The 2.8, I mean, it really is like 0, 0, 0 in my calculator, times 10 to the negative 4. There's the hydrogen concentration. If I plug that in my calculator, I get about 3.55. Okay, so there's everything they were asking for. We got the pH, and we got the concentration of all 4 particles in the solution. What if they would have only asked for the pH? Make note of this. If you have a polyprotic acid, and especially in this case, let's say it's weak, the most significant source of hydrogen is the first dissociation. If I would have just gone opposite log of X right away, it was virtually the same thing. I mean, yeah, it created a little bit extra from the second step, but with a reasonable amount of sig figs, it really didn't even change this value. So for future reference, if you have to calculate just the pH of a weak polyprotic acid, you can just do the first ice table, and that amount of hydrogen is the significant source of hydrogen. You can go opposite log. Now in this case, we had to do the second ice table because that's the only way that we would have known the concentration of the carbonate ion. That doesn't show up till the second dissociation. So in this case, we had to do the second. So that wasn't all a loss. It wasn't a total waste of your time. But make note, if all you needed to do was calculate the pH, you can just do the first ice table and go opposite log of that hydrogen concentration. The amount that we got from the second was insignificant.